answer. But still, I actually did make money doing algebraic geometry at one point, so I get to tell you that story. It's a lot of fun. All right, so let me start this. I'm going to try to do a combination of the algebra and the geometry, and since I don't want to write a lot of equations, I'll draw my hands and wave around a lot, and then we'll be able to think about the geometry a little bit more than the algebra. So I want to start by asking you, what do you get if you intersect two spheres? And I just mean ordinary spheres in like three-dimensional space. What can you get? A circle or a point? How do you get a point? Yeah, so if the two spheres are touching at just one point, then you can have that. So the intersection can be a single point, a circle, or nothing, which also looks round, so it fits in the pattern. Or of course it could be a sphere if the two, if it's actually the same sphere twice. But this is the usual case, right? This is what we usually expect to get as the intersection of two spheres. Now let me make it a little more algebraic than just the geometric observation. When you get a circle, it's because you have two spheres kind of like soap bubbles or something, and the circle of intersection, well, it's like a circle is supposed to be. It's all in one plane. And you can get that as soon as you write down the equations for these two spheres. What's the equation of a sphere look like? What kind of equation describes a sphere? Equals r squared. Okay, so you chose to put the origin, the center of the circle at the origin, and you allow the radius to be whatever. But of course, in order to do that, you've committed what the Greeks would consider a heresy, which is you've introduced coordinates into the system. And that takes away all the pretty pictures, but it does allow us to do some computations. So when we introduce the coordinates, we do have to make some choices. You decide to set up your coordinate system with the center of one of the spheres being at the origin. If you're in the process of making your coordinate system, you might as well eliminate a little bit more ambiguity and say, well, I'll find the center of the second sphere. I'll draw a line that joins those 2 points. That'll be one of my axes, say the first coordinate axis. I can let this distance be 1, say, or normalize it in some way like that. And then this would be the equation of the first sphere, and the equation of the second sphere would now look like this. So I got two different radii, potentially. And, well, I think I normalized it differently from what I said. Well, anyway, so once I have these two equations, then these are equations that regulate the x, y, and z coordinates of the points that are on the intersection. The points on the intersection have to satisfy both of the equations. So those points, x, y, and z, will be points that make both of these equations true, and then in addition, any manipulations that you do to these equations would then be another equation that's going to be satisfied by those same points. So in particular, you can take these two equations and subtract one minus the other one, and you discover that 2x minus 1 equals, which way did I subtract? R squared minus little r squared. And this is now the equation of a plane in three-dimensional space. So the intersection of two spheres is a circle. In part, what that is relying on is the fact that the intersection of the two spheres will also lie in a plane. So there's a plane that contains the circle, and I've already given you an equation for it. Very well then, what happens when you intersect three spheres? What do you get as the intersection of three spheres? Come on, it's not that hard. When you intersect the first two spheres, what have you got? Well, you've got a circle, yeah. But that circle is part of a plane. So now intersect the first and the third circles. You expect that to be, first and second spheres intersect in a circle which is part of a plane. First and third spheres also intersect in a circle which is part of a plane. So the intersection of all three of the spheres, it now has to, in particular, lie on the intersection of two planes. If I'd have written out the equations of the three spheres this way, I could subtract them in pairs and I'd get two equations that are linear in the three variables. Each one of those equations would describe a plane, and then the solution set has to, in particular, satisfy both of those equations. So it lies in the intersection of two linear hypersurfaces, which are two planes, and the intersection there is a line. So the intersection of all three spheres has to be part of a certain line. Well, I think you can see what happens when you intersect a line with a sphere. What do you get if you intersect a line with a sphere? Typically, 2 points, right? I mean, it could be no points or just 1 point or something like that. But it will be 2 points. And in fact, if you play around with the equations and you allow complex solutions, then you will, in fact, always find 2 points or a double point or something like that. So a little bit of geometry combined with the algebra helps you find what you're interested in. So as soon as I intersect three spheres, then I'm down to just a finite number of points. In fact, what we expect is it to be 2 points. Could be 1 or 0. And again, there's going to be degenerate circumstances where the first two spheres intersect in a circle, and maybe the third sphere also passes through that circle. It has a different radius with a different center that's on the same line as the other two centers. So other configurations can happen. There's a certain kind of degeneracy. 4 spheres, what are you going to get if you intersect 4 spheres?
Nothing.
Probably nothing. Probably nothing, because, well, I mean, you're down. Once you intersect the first 3, you're down to just 2 points. So unless your sphere just happens to pass through one or both of those points, you're not going to get anything. And in general, you're not going to expect something from the 4 equations of the spheres. You'll have 4 quadratic equations. One way to play around with the algebra there is to say, aha, any point that's in the intersection of all 4 of those spheres would have to have x, y, and z coordinates that make all 4 of the equations be true. I can take those equations in pairs, subtract them, and get 3, 1 less than 4, 3 linear equations in the 3 variables that you would expect each one of those determines a plane, and the intersection of 3 planes would be just a single point. And now I have to go back with that single point and check to see whether it actually satisfies the original quadratic equations, and probably the answer is no. All right, so that's fine. We played a little game with intersecting spheres, and we're like, okay, we saw some connection between the geometry and the algebra. You didn't say anything yet about profit, but let me point out an example where you might be interested in the intersection of various spheres. Let's see, how can you describe in words what it takes to be, what is a sphere? I mean, what are the points that make up a sphere? How do we define a sphere?
4 points, 3 space, effective distance from the fifth point.
That's correct. So it's all the points in 3-dimensional space that are of a certain distance, not just equidistant, but I'm going to tell you the distance in advance, from a certain point, which again I'll tell you in advance. So you say that you're on a sphere as long as you know that you are this far from that point. And now that describes a certain sphere. So if I told you that you were this far from that point, and this far from that point, and this far from that point, well, on the one hand, what I've just done is I've described myself as being on the intersection of 3 spheres, which is the same thing that we just calculated down here. But on the other hand, what I've just done is I've sort of described my position. This is exactly what happens when you use a GPS. Your GPS is actually doing some pretty snazzy calculations, which, by the way, involves things like the theory of relativity, to determine exactly how far it is from a bunch of satellites that are floating around in space. Not just 3-dimensional space, but, you know, outer space. And according to these calculations, as soon as you know your distance from just 3 of those satellites, you will have put yourself in the intersection of 3 spheres, and the GPS will know where you are up to 2. There's an ambiguity of 2 points. If I know my distance to a 4th GPS satellite, I will then be able to pick out which of the 2 points it is. As we said, in general, you don't expect the intersection of 4 spheres to be anything at all. It's an empty set typically, but if you know that you really are standing somewhere, then there is at least 1 point on the intersection, and unless you just happen to be in a kind of a degenerate situation, if the satellites just happen to be all in a row or something, which they won't be because they're all following the same orbit, then you would expect to have no ambiguity left. As a bonus, actually, what you saw me doing with the algebra over here, you saw me try to visualize the intersections of various spheres as being parts of planes in three-dimensional space. As soon as I know my distance to 4 of the GPS satellites, I can describe my location by saying I actually land inside 3 planes. 3 planes will intersect in a unique point. And moreover, finding that point is actually quite easy. That's solving 3 linear equations and 3 unknowns, which even our freshmen and high school students can do. Okay? Somebody know how many GPS satellites they actually have?
6 over the planes, and each one should have 4.
How many?
So 4 times 6.
Why is it 4 times 6?
But I mean, there's 6 orbital planes, I know that for sure. And then I think they have 4 satellites on each.
Well, I didn't know that actually. They have them in separate orbital planes?
Yeah, so they have 6 planes, so they separate the space on our system to more or less symmetrical ways.
Oh, that's cool. I didn't know that.
Well, I mean, the thing is, a lot of satellites are not operational.
Well, a bunch of them, that's right. There will always be problems where, you know, of course they're always worried, these are military things, so they're worried about the enemy taking out your satellite and stuff like that. Plus, don't forget, it doesn't help us a lot if one of the satellites is, oh, let's say, way down there on the opposite side of the Earth, which of course the people in Australia need it right this minute, but it doesn't do us any good. So, yeah, there's a couple of dozen floating around, and at any point, due to questions about the Earth getting in the way or other limitations on your field of vision, you could expect at most a handful to be, you know, able to check your position. But usually your GPS device will be able to pick up, let's say, about 6 of those things. And then you end up trying to solve 6, well, let's see, if you get 6 satellite distances, do pairwise subtraction, you'll end up with 5 linear equations to solve and 3 unknowns. That's actually an over-constrained system, but take a numerical analysis course and they'll try to help you find the thing that's closest to a solution to an over-constrained linear system. That's a pretty well understood mathematical problem. Okay? So that's how they can get such good accuracies. They have a little bit of redundancy in the initial data by collecting extra information from additional satellites. All right? So the takeaway from all of this stuff is algebraic equations, polynomial equations in multiple variables can help us describe geometric situations that might be of interest to us. And that's the kind of thing I have in mind when I talk about algebraic geometry, real algebraic geometry helping us solve real problems. Two uses of the word real. All right, so now let me give you another one. And this one was introduced to me by a guy I met at the IMA one time. His employer was not a university. He was an algebraic geometer. He was working for GM, you know, the car company. And I said, okay, I give up. What do you do for GM? And he said, well, my last project was to design windshield wipers. And I said, really? Okay, so show me, guys. How does a windshield wiper clean your windshield? Use your arm. Come on. Yeah, okay, so, well, you didn't quite do it, what everybody else did. So everybody else does this. This is what I thought. And he said, no.
That's a joint.
Yeah. They don't, well, so you can have 2 of them and they do this. Okay, and actually in the old cars, you look at those movies from the 1920s, they did that. That was perfectly reasonable. But he said, go out and look in the parking lot. I had to do that. I left my talk with him, and I went outside, and I looked in the parking lot. Sure enough, windshield wipers don't do this anymore. There's some kind of, like, typically a jointed assembly, and you have the stick part of the windshield wiper. It's on a slant from the other part. And there's very good reasons for this. If you have a single rotor that's moving your stick back and forth on a plane, and then you attach a single wiper blade to it, all you're going to be able to trace out will be, well, who knows? What kind of surface can you trace out with that? A portion of a? Sector of a, well, I need something two-dimensional. I need a surface. A circle, huh?
A disc.
Yeah, a portion of a disk, that's right, which lies in a plane. Well, that's actually the wrong answer. Because if your thing is pivoted a little bit, you could have a piece of a cone. But if you are, if your windshield is made from a bunch of line segments that all pass through a single point, which you're tracing out as a cone, you could, if you wanted, have your windshield with a little bit more complicated, not a single rotor, but you could kind of have it like weave in and out and get what a topologist would call a cone. That's the cone on a curve. Topologists are just that way, right? But it would be a cone on a curve. In other words, you take a curve and a point that's not on the curve, and then you draw all the line segments that connect the point to the points on the curve. And topologists call that a cone, and no one else does. So a single windshield wiper blade could do that. But that's not how windshields look. In those movies in the 1920s, the windshield wipers were doing this over a plane. So the windscreen really was just a flat piece of a plane, and then it was easy to clean them like this. Well, now they're kind of like this. So we had this little discussion, and he said, well, you see sometimes people make like these futuristic designs where the windshield is going to be like a portion of a sphere, a little bubble. He said, how are you going to clean that? You can't clean something that's spherical, because you're not with a standard kind of a windshield wiper blade. You want something that's flat. Well, so what are the surfaces that you can make that can be made as collections of straight line segments? Imagine all the points that your windshield wiper is going to touch at some point, at some moment in time. That's going to be a collection of line segments. What are the surfaces that you can make that are out of an assembly of lines? Anybody know a name for those?
Polyhedra?
I'm sorry?
Polyhedra?
Oh, a polyhedron would do it. You're thinking, yeah, those are line segments. So she's actually taken flat planes and glued them together. That's true. Wow, I never thought about that. You could have like I guess I would call it a dihedral windshield, right? So it would be two planes put together, and you have your bottom one going like that, and your top one going like that. Yeah, that's pretty cool, actually. I think I'll put that in my next make-believe car. No. There's a word for surfaces that are technically they're just unions of lines. Ruled surfaces. So look these up sometimes, and they include cones, for example, but cones are collections of lines that all have a point in common. There's no reason that you necessarily have to have a point in common. And in fact, as you watch your a modern windshield wiper go across the screen, it keeps passing through different points all the time. You sort of ignore where the rotor is attached, and you just see the line segment of the wiper blade, and it's just like a moving line, and yet it manages to cover the whole surface. I'll give you one interesting example of a ruled surface, and I'll let you play with how you might actually make a windshield out of this. You know this surface? Let's see, I guess we have the one of one sheet. So what does this one look like? A what?
Triangle.
No, that's the hyperbolic paraboloid.
Oh.
That's the saddle surface, right? Why do they call it in the calculus books? They call it hyperbolic paraboloid. The kids never remember that.
Okay, yeah, okay, it's like this. Nuclear reactor.
Nuclear reactor tower, yeah. So it's this thing here. So your windshield could be made out of something like this if you wanted, because this is actually an assembly of straight lines like this that kind of wrap around. And you can see this if you ever take the two discs and parallel to each other, and then you just put strings up and down to connect them, and then you give it a twist like that, and you get exactly the surface. And what's funny about this particular surface is I believe it's a theorem that these are the unique surfaces which can be made as a collection of lines in two different ways, because you get the exact same surface if you do that. So this same surface has lines that go that way. So you could have your windshield wipers like this, then you could have a backup set that do that. Anyway, so this gets you to the question of, well then, okay, once you know that you have a windshield that actually is a ruled surface of some type, so that you know that it can be constructed as a collection of lines, then the question is, well, how do you actually get the windshield to go across, the windshield wiper to go across your windshield so that it, at every moment, is lying in one of those lines? You have to kind of parameterize that set of lines and get your thing to move across in that way. Well, go look on a modern car and you'll see that they figure out ways to do it. They still make a lot of cars still just have a single rotor that goes back and forth, but at the very least they keep the second part tilted, that the actual blade is tilted relative to the point where it is joined to the stick that goes down to the motor. So you manage to sweep out a collection of lines that are not all going through the same origin. All right, so, well, he and I were hanging out for a few months there. So he talked about other things that they do over at GM, and I was actually pretty impressed at how much math is involved in a modern car. So windshield wipers led then to this other discussion of linkages in general. You see, when you want to make a windshield wiper that has some kind of a linkage, there will be a little motor that's moving a stick back and forth. And the position of that stick will vary in time, and you need to keep track of it. So one way to do that is to watch where the endpoints are, where the endpoint of that stick is. Again, I'm going to do the same thing I did over there, which is to start to introduce coordinates. You put some coordinate frame right through this point, call that the origin, and this point will then have x, y, and z coordinates. And those coordinates will change over time. Is there anything that you can tell me about these coordinates that will not change? Their distance from the origin. Well, I mean, I guess you could have something on a sort of a piston, and that would be an interesting kind of windshield wiper. But the position of this point will always, it'll be a set of three numbers, x, y, and z, but you'll have x squared plus y squared plus z squared come out to be one windshield wiper arm length, one unit. Then if you wanted to get some sort of more complicated construction, you could say, okay, and then I'm going to attach to that another bar. Maybe you'll have a little motor here that would allow this thing to swing back and forth in some direction. Maybe you'll have it linked rigidly so that there will be a fixed angle in there. You could have some sort of a complicated thing where there's a multiplier effect so that every angle change here will give you a similar or greater or smaller angular change. You know, you have those little like pantographs. I don't know if you guys know what those are, but you move something and something else moves faster or slower. So you are going to get another point, x prime, comma, y prime, comma, z prime. And depending on how exactly you set up the linkages, you might know several things about this, but one of them that you will know certainly is that when you look at the distance from the new point to the old point, that's going to stay fixed because you hooked them together with a solid bar. And so now you have two equations that link these things. This won't necessarily be one anymore, but it'll be some distance away, and that's not going to change. So suddenly you start to see that you can describe things of interest like the motion of your windshield wiper blade by writing down systems of polynomial equations. In this particular case, these equations aren't going to completely constrain what can happen because you might, for example, be spinning this thing back and forth with only a single axis on a motor, in which case the x, y, and z will satisfy a linear equation that puts them in a certain plane. So there will be additional equations that you can write down. So some linear function, for instance, might be 0. But this now gives you a mechanism to describe a lot of motion problems, linkage problems, and it doesn't necessarily have to involve a lot of r's and thetas. You can do everything polynomially. Okay, and now I'll take a little side route here through a bit of the current theory on this. When people do find themselves facing long strings of polynomial equations, then the question is, well, what can we conclude from them? When you have linear equations in several variables, you guys have been told about several things that you can do to solve those linear equations. One of them, for example, is row reduction. So you know that you can take 5 equations and 5 unknowns, and you subtract off the multiples of the first equation so that it stands there with the x still in it, but all the other equations no longer have x. You just have 4 equations and 4 unknowns. And you sort of work your way down, you get a diagonal thing. Then you can choose to either completely diagonalize your system or solve for the last variable and work your way up. Okay? Now those of you who have taken a numerical analysis course know that that actually sucks because it's subject to a lot of round-off error and that sort of thing. So you have the LU decompositions and things like that. For polynomial systems of degree higher than 1, so if you don't just have linear equations but quadratic equations, you can try to do something similar, but there's a lot of things that can get in your way. A tool that has been in use for about 30 years, it's got certain drawbacks, but it works pretty well in situations that don't get too complicated. I'm not going to go into the details, but I'm just going to give you the name here. It's fun just because it's fun to say. It's the theory of Gröbner bases, and there's an O with an umlaut, so you get to say some nice German sounds. The Gröbner bases ask you to find new bases for your ideal of all the polynomials, hoping that it can be changed into a kind of a nice simple form, sort of like what you do for the row reduction of linear equations. You look to see if maybe you can get one of the equations to involve just one of the unknowns, and then another equation or two that might involve a couple of the unknowns, and sort of work your way back, getting a kind of what they call a triangular system. So people who are describing linkage problems have come to see this as a useful tool. They describe their problem by writing down systems of polynomial equations, and then when they're looking for what the solution is, how the solution is going to behave, they turn to the people working on this or other related techniques for rewriting the collection of ideals, the collection of polynomials. These generate an ideal and a polynomial ring, for those of you who know what that means. So this is just giving you a new basis for the same ideal. Let me give you another linkage problem. This one doesn't have to do with cars. It has to do with bioengineering. I happen to have another linkage handy. I carry it with me at all times. It's this one right here. So if I want to describe where my elbow is at any moment, I would set up a coordinate system right through my shoulder. I would call this the origin. I would probably set up my coordinates to be, I don't know, x is that way because that's the easiest way for me to point, and then y, and then z, and I'll let this be my unit of length. So now this thing suddenly inherits coordinates, x, y, and z coordinates, and about those coordinates I certainly know one thing. X squared plus y squared plus z squared is equal to 1, because my elbow will, unless I've done something really stupid, never become further away from my shoulder than... Okay, I learned a lot about shoulders because I did have to have my shoulder sort of reconstructed at one point. So one of the things that you learn is that this elbow does have a pretty good degree of motion if you're healthy. It can travel to a lot of points. You can't actually get this elbow to travel over the entire unit sphere. Okay, good. So at least you see that there is a constraint. Can you describe algebraically what the constraints are? Some of the constraints anyway. The first pass at your constraints. X, y, and z coordinates. You can't think of anything? Oh, yeah, right. The x coordinate can't be negative. It's the x coordinate that can't be negative. I mean, you can go a little bit negative, but it's kind of hard to do that, right? So there's some constraints on these coordinates. When the x coordinate is very large, of all the points on the unit sphere, the points with a large x coordinate, you actually you can rotate over the full circle. But then if you imagine trying to trace out circles of bigger radius, in other words, decreasing x coordinates, at some point you find it to be more and more difficult. All the shoulder muscles and stuff get in the way when you have a very small value of x, and so now there's some inequalities on y and z that are related to the small x's. And certainly once x gets to 0, I can't do that, right? And negative x's are even more difficult. But that's only the first stage of a linkage. I could give x, y, and z coordinates to my wrist as well. So now I have a total of 6 variables that can help me describe how the first 2 links of my arm are behaving. And then the x, y, I might be most interested in where the wrist is. In other words, the x prime, y prime, and z prime might be the thing of greatest interest to me. But I can't really describe that easily without introducing this intermediate variable of the coordinates of this point. And if I wanted to talk about the positions of my hand and so on, then that would be even harder. But by introducing a lot of variables, I can actually describe where all the different parts of my body are, and I can watch them move around in space, and then all of those different coordinates become functions of time. They're not independent functions, however, because they're still subject to these constraints. X squared plus y squared plus z squared equals 1. The difference between these 2 positions, that length has to be whatever the length of my arm is, and so on. You do now have a way, though, to describe motions of all parts of the human body as they wander around through space. And in particular, you can use those coordinates to help you with another little bit of classic mathematics that I'll really throw in here. And it doesn't really have anything to do with algebraic geometry, but I thought it'd keep you entertained. So I have brought a little plate, which I have put a couple of things on to help you keep track of its orientation. So orientation is one of the phenomena that you need to keep track of if you're going to be worrying about moving linkages. I might say that the plate where it is right now and the plate where it is right now are oriented in the same way, although I've translated it. So, but you keep track of the position. I mean, the first thing to notice is which way that pencil is pointing. And I can point it towards any of you. And that make that point, in fact, you can just sort of describe where the pencil is going by specifying like the latitude and longitude of where it's pointing to on an imaginary sphere centered at the apex. You astronomy type people, you'd be thinking of azimuth and declension, or what are those two things you use to keep track of positions in the sky? Okay, so a couple of numbers anyway would help you keep track of where the pencil is pointing. Of course, I would change the orientation if I did this. It doesn't change the pencil, but it does change what I would call the orientation of it. You see the little smiley face is looking different. Well, that can be kept track of by sort of monitoring the position of the green dot, the green spot there at the top. I have it at the top right now, but if I start doing some rotations, it doesn't have to be at the top. But apart from making it point towards a different person or rotating it as it points to that person, I don't see what else I could do to change what I would call the orientation of the plate. So 3 numbers, like latitude, longitude, and rotation angle, those 3 numbers would help you keep track of your orientation. So we describe orientations as with 3 coordinates, if you like. The set of all rotations, it's perhaps more mathematical to describe them with a 3x3 orthogonal matrix, special orthogonal matrix. So the collection of all of these things is actually a mathematical group, SO3, a special orthogonal group of in 3-dimensional space. But that is, in fact, a 3-dimensional Lie group. And the reason you know it's 3-dimensional is because you can tell which way you're going with just 3 numbers. 3 coordinates helps you keep track of that. There's a funny fact about SO3 that I can tell you, which will be of interest to those of you who are algebraic geometers, and that is it's not simply connected. As a topological space, it's not simply connected, and I am about to demonstrate to you an element of order 2. For those of you who don't, you already know what I'm going to do. Yeah, so this is the plate trick. Watch this. Keep an eye on the plate. It currently has a certain orientation. Right now I got the pencil straight up and I got the green thing to you. Now I'm going to move it in space, but pay no attention to its translations, but do keep an eye on the different rotations. Every time I do something, I've moved to a new spot in SO3. I've given a new orientation to it. And as time goes on, I'm going to gradually change its orientation. You'll notice that, just to keep it really clear, I'm choosing only orientations that point straight up, with the pencils pointing straight up. But the green dot is going around at 360 degrees, and I'm just about there. I've done a full rotation. So there was a little path through SO3. You saw me give a changing orientation as time went on. That doesn't, it looks like I've, I don't know, changed things around here. I can actually do a 720-degree rotation, and it doesn't consist of just getting more and more twisted all the way through my feet. There's a way to continue to rotate in the same direction by lowering the plate as you go. But you'll notice if a person were looking down from the sky and didn't see how high the plate was, they would have always seen the pencil pointing straight up, and they would have seen the green dot just go around once and then go around twice. And along the way, I have traced out now the same path in SO3 twice. Well, I could have taped one of these little smiley plates to any portion of my anatomy. I could have had one here on my wrist. I could have had one on my elbow, my shoulder, my hip, my foot. And at every point, it would be picking out for you an element in SO3. As time went on, all the way through that double little twist, every one of these little plates would have been recording a path that went through SO3. Since I ended up in exactly the same position I was, I mean, my entire body is resting in exactly the same way that it was, every one of those little plates would have come back to where it started. In other words, every one of those plates now described a closed loop through SO3. But on the other hand, if you watched where this plate and this plate and this plate went, they would have been traveling very similar paths. So the collection of all those plates from my fingers down to my feet would have traversed a homotopy between the 720-degree loop at my wrist and the constant path at my feet. So that shows that the 720-degree loop is actually the trivial loop in SO3. Okay, it's harder to show it's not that the 360-degree twist is not trivial. So that is, in fact, a non-trivial element of order 2 in SO3. All right, that I know just went over the heads of a lot of you, but it's a fun little thing to try. I know from experience, don't try it with a full cup of water your first time. Don't even try it with a glass because it gets really bad. All right, let me describe for you some more of these motion things that can be treated with algebraic geometry. And I want to turn next to the one that was the illustration that I gave Corey for this talk. And this is the one that's used in flight simulators. Those, not just the real ones, but the toy ones, like when you go to like Main Event or whatever, and you climb in there and the thing like jerks all around and stuff. So what these things try to do is they try to let you kind of get an object like this, like you're going to walk in there and sit in there, and they want to have it be able to kind of like fling around in space. One of the things that we'd like to keep track of when we do that is just exactly how is the thing set up? How is it oriented? What is its... Not oriented isn't the word I want to get. How is it configured right at this moment? I mean, I'd like to say that this is different from this. It's also different from that. I mean, how many things am I going to have to keep track of to keep track of all the different ways that I could arrange this thing in space? One of the things that I could do is I could, tape one of these things to it and then say, oh, well, if you just start doing any of these motions, you're going to give me an orientation, a different orientation. So as you try to keep track of exactly how you've flung the thing around, one of the things that you'd keep track of is the orientation. That it requires 3 coordinates to keep track of that. What else am I changing besides the what else could I change besides the orientation as I start moving this thing around? How else could you keep track of what else I'm doing?
Position?
Yeah, the position. Well, how do you describe this with like a single number? I mean, a single position of what? I mean, I want to have coordinates or something, but... Huh?
Center of gravity.
Okay, center of gravity, I'll take that. Okay, it kind of doesn't matter, actually. You could take this point over here or that point. But pick a point and watch where that point goes. And then once you've picked, I'll take the center of gravity. Once you've picked out where the center of gravity has gone, then you could think of anything else that you might do to it as just being a change in its orientation. All right, so the complete range of motion of what you'd like to do to something like this, or to a flight simulator, an imaginary cockpit that you want to train pilots, is you need to be able to account for 6 independent variables. 3 variables that would give you a change in the position of the center of gravity, and 3 more variables to keep track of this change in orientation. Where is the latitude and longitude of the pencil, and what's the rotation of the green dot? All right, there is a way that you can do this to the poor suckers who are going to have to climb into the machine. What you do is you build the following kind of a shape, the following kind of a machine. It takes some doing to draw this, but I think I've got it right. So I want you to have 3 points on the floor. There's 2 of them. And here's the third one back here somewhere. So 3 points that are going to stay glued to the floor. And then you put pistons attached to these points, attached in kind of like a ball and socket joint, like your shoulder. So it can rotate around in any kind of direction. And because it's a piston, unlike the linkage arms I was talking about before, you can change the length of it. But you take 2 pistons, one on this side and one on this side, and you have them meet up in space somewhere. Then you take a couple more pistons, join to the next pair of points, and you have them come up into space somewhere. And likewise, this third pair of points, you have them joined by pistons at a third point. So just to recap here, points A, B, C are fixed, and points D, E, F are allowed to move. But you don't let them move independently. Instead, you hook these onto the bottom of your flight simulator, so there will be a plane. Any 3 points determine a plane in 3-dimensional space, a unique plane unless the points are collinear. So there'll be some plane down here which will become the bottom of where you put your chair. And then here's the chair. And here's some poor slob that has to sit in this. And now what you realize is that if you start changing the lengths of these 6 pistons that I just put in there, you're going to make the chair jiggle around. It's important to realize that if you kept 5 of them fixed and you just moved one of them, everything would have to shift just a little bit. But you could do it. If you change just one of these lengths, like if I tried to make the line segment AE longer, what will happen is the other line segments don't have to change their length, but if AE gets longer, then the thing will kind of tilt that way into the next room. Okay? In fact, the way I would describe this is that there is a function that you can compute that would take the lengths of these 6 pistons, so that's a function defined on our, well, on the, I guess lengths have to be greater than or equal to 0. But take those lengths and somehow you would compute 2 things, the center of mass, the center of gravity of the object, and then independently you could compute its orientation, which is an element of this group that I called SO3. Okay, which you can think of this as being locally a 6-dimensional, it's a 6-dimensional manifold. So locally it's described by 6 coordinates. It's not exactly clear how this function is computed. It's actually easier to think about it the other way. You could think, oh, maybe I should have put the name of the function here, because it's perhaps easier to go this way. You say, dang it, I want the guy to be like this. So you get a bunch of assistants to run out to the platform, and then you say, okay, hold it. No, you, over here. No, you raise your arm. Yeah, just like that. And then you get somebody to measure the 6 distances, and you write them down. And so if you know where you want the center of mass to be, and you know how you want the thing to be oriented, then you can compute these 6 distances. But that's the way it's easier to understand this function. That would be g, and then f, I need f to be the inverse of this. Fortunately, when you take the function g, you can write it out in local coordinates. Use those 6 coordinates to figure out the function, also expressed in terms of 6 coordinates. The 6 lengths of the rods, you'd see that this function g has a derivative which is almost everywhere invertible. It's a 6 by 6 matrix whose determinant is generically non-zero. And by the inverse function theorem, that means that there will be an inverse, at least locally. If you've got a configuration and you want to move it to another configuration, then you can at least get started heading towards that new configuration. That's what it means to be locally invertible. All right, so that's it's kind of going to work out because you have as many degrees of freedom as you told me that I had with the stapler. That's 6. I've managed to match that with the number of things that I can vary on the levers, which is also 6. And as I said, I can actually check that generically the function g is 1-to-1. So basically, you can get all the motions that you want by wiggling around these levers. And you can even describe the equations that you would need to solve to determine where the object would end up if you set the positions of the levers to some numbers. I mean, it's hard for me to describe the exact configuration of the thing this way because I have a three-dimensional manifold that's not just R3. But an easier way to do it is to think about a function that takes the 6 lengths. Well, you know what? I'm not going to do it in terms of functions. If I knew the 6 lengths, then one way that I could do this is I'd say, all right, you know what? I will know exactly where everything is going to lie in space if I can just determine the coordinates of those 3 points. So if you call these points x1, y1, and z1, x2, y2, and z2, x3, y3, and z3, and these points, you'd have to give coordinates to these. For simplicity, I just decided to let this one be at the point 1, 0, 0. This one is at 0, 1, 0, and this one at 0, negative 1, 0. Then, if you knew the 6 lengths of these rods, which I called Lij, the I is for which of these 3 points it's attached to, and the J is which of those 3 points it's attached to, then you get equations like this. x1 squared plus y1 minus 1 squared plus z1 squared equals L12 squared. There is a similar one for x1 squared plus y1 plus 1 squared plus z1 squared minus L13 squared. And then you'll notice that the point that I labeled D up there, that's the one that has coordinates x1, y1, and z1. It was attached to the points. Oh, did I draw my thing right? I put the coordinates on the wrong points, A, B, and C. Ignore that. I meant for that point D to be attached to 0, 1, 0, and 0, negative 1, 0, but it's not attached to the third point on the bottom. So you have two equations of that type. You have two more equations that involve x2 x2 minus 1 squared, etc. x2 is mapped to two of the points on the bottom, and x3 is connected to 2 points on the bottom. 6 rods gives me 6 lengths, each one of which is determining a certain distance. In other words, the points D, E, and F are floating inside spheres. Each one of them is in the intersection of 2 spheres. These things tell me the lengths, the radii of the spheres. And so if I hold these things, if I hold a couple of these things fixed and I let the other ones vary, then each of these points would be traveling in that circle. You guys told me that the intersection of 2 spheres would be a circle. I see a little bit of a problem here in actually trying to figure out how the heck the thing is oriented when I tell you the lengths. I used all of these lengths to write down the 6 equations that involve the lengths, but now I have 6 equations in 9 variables. It seems a little underdetermined. What additional information do I have in the picture that I haven't put down in my equations yet? Anybody see it? There's some certain... Right, the distances between D, E, and F are going to be fixed because I remember I attached those, I made those ball and socket joints, but they're put in here on the bottom of a board somewhere. And so once I have constructed the device, then those distances are fixed. So in addition to these, you're going to get equations of the form x1 minus x2 squared plus ... equals whatever that distance is. And so there will be 3 equations there representing the lengths of these sides of the triangle. All right, so now you have 9 equations and 9 unknowns. But the key thing is that they're all polynomial equations. So if these numbers are all known, then that will help you determine what those numbers are. In terms of algebraic geometry, I'll tell you something very interesting. The solution set, once you have the same number of variables as equation, you kind of expect that you have what's called a zero-dimensional variety, which is a fancy way of saying there's only a finite number of points. Like when I intersected the 3 spheres, I got 2 points, not a single point, 2 points. People worked on this. This device is called a Stewart platform, and it was developed about 50 years ago. People kind of wondered like if there could be multiple solutions to these equations, and they started to find cases where they'd have multiple solutions. And then the algebraic geometers would wonder about just how many there could be. And about 20 years ago, that was settled. It's possible for sort of the generic combination of these lengths will give you 40 different solutions. And it's possible for them to all be real solutions. So you can actually find, there's a guy named Dietmeyer that has a paper on this published in the mid-1990s. And he's got a little picture of 40 different configurations of the stupid platform, which involve exactly the same sets of the 6 different lengths. So it's some interesting algebraic geometry in there. I'll also point out that topologically, there's some constraints involved in this one, the same as I have for my arm. Once you start lengthening things too much, you start to realize that the machine is going to break. If you try to lengthen one of the pistons too much compared to the other 5, you're going to violate the triangle inequality. Or as you start to make your degrees of motion, you'll see that the pistons try to cross, or they'll smash into the ship, the platform. So there's a bunch of inequalities in real life, but at least the algebraic geometry goes like this. Okay, is that fun? Now you're worrying about the profit. Where's the profit? Okay, I got one more application. I got enough time to give you this one. And it's described by polynomial equations too. And this time I'm going to give it to you in reverse, because that's the way it came to me. Instead of somebody saying, hey, I'm trying to model an arm, or I don't know, whatever it was. They say, I was reading how I used to do this all the time. I would just sort of sit around and read math discussions on the internet. Yeah, because no social life. And then, so one day I just saw this when somebody said, hey, I got equations like this. I forget the specific numbers, but he wrote in, and it's a bunch of these quadratic equations. And he said, can anybody tell me if there's like a unique solution to this system of equations? Well, I don't know. I'll tell you what. I'll pass this around, and you can take a look at it if you want. But I'll tell you in advance, there are 19 variables and 20 equations. So it's a little bit over-constrained, first of all. I think actually the way it first was given to me, he ripped off one of the equations because he knew that that would be over-constrained. He thought maybe 19 and 19 would be the good match. Well, if you look at the equations carefully, you'll notice that they look like a bunch of distance things. It's just the same as all of these things. It's something about spheres with different centers and different radii. But there's something about the structure of like which distances do you know? Like in this case, I didn't know the distance between every pair of points. At no point did I ever mention the distance between A and C, although I guess I could have calculated it. But there was no variable piston that went from A up to F in my picture. Okay, so not every pair of lengths is involved in one of these problems. Well, I worked on it because, you know, I like math. So I played with the equations a little bit, and I discovered, somewhat to my surprise, that there was some redundancy in his equations, and so there wasn't a unique solution where he expected one. But I tried to do some numerical calculations so I could actually demonstrate what it turned out that there was a whole path's worth of solutions. You could take a small perturbation of any one of the variables, and then all the other variables would have to change, but they could change. There was a consistent way for everything to change at once. So in other words, you could imagine some of the points kind of moving around in space with the lengths changing or not changing in the way that he said. I think the lengths had to stay fixed, and then but the points, he didn't know where the points were. And so I had this vision of kind of like a monster kind of walking around with, I don't know, distances. Because if you look at the equations, one of the things that you'll notice is that it's a sequence of distances. Every one of the equations says that a distance has to be something. But it's always involving one of several points that's out in three-dimensional space, a distance between that and a point that's in the plane. So now it is a question of like, you know, a monster walking around because you have distances that's on the floor where you're going to step versus parts of the anatomy or something. But actually, I got a better model of it. When I realized what I was looking at, I thought, I know what's going on. In fact, I was so excited. I told my kids at dinner. They were little. They listened to their dad back then. And I said, so I tell you, it's kind of like he probably works for NASA. Because what he's got is a bunch of lunar rovers that can't talk to each other. They're all on the surface of the moon, but they can't communicate their distances between each other. And you know, he's got these lunar orbiters that are up in three-dimensional space somewhere, and for some reason they can't talk to each other either, but they can talk to the ones on the ground. And what he's trying to figure out is, if you know all of the distances from the orbiters to the rovers, can you get it all figured out? And I thought that was pretty cool. What do you think, kids? And they're like, yeah, Dad. Okay, cool. NASA, whatever. So I wrote back to the guy and I said, okay, there's not a unique solution. Here's a family of points that all have the right interpoint distances, and I envisioned it was something. And by the way, I told my kids that you probably work for NASA because orbiters and rovers and stuff like that. Well, I got back a response by email, and you can tell in the email that he was laughing. He was like, no. He said, it's not NASA at all. He says, I work for a commercial lighting company. We do stage lighting. He says, we sell lighting devices to rock stars who are going to walk around on the stage. And the way it works is they put a belt on them that has a transmitter, and then there's receivers that the road crew throws up into the rafters. And we've already figured out, as I showed you guys an hour ago, that if you just have the distances between each one of the belts, and you need a minimum of 3 things up in the rafters, with a 4th one used to give some numerical accuracy to it. At that point, you'll know exactly where the performer is, and we have a light on each one of the things in the rafters that can be moved to shine on the performer. So as the performer walks along the stage, then the light does its thing. And so he said, the problem with our system is we've got it great, we can market it to all the rock guys, but the problem is that when they go from town to town, which is like every night they're traveling to a new town, the road crew has to throw the the receivers up into the rafters. And we got to know where those things are so that we can correctly do all the calibration. Like in the initial things that I did, you can triangulate your position just fine, but you have to know where the centers of the spheres are. That's the transmitters, I mean the receivers up in the rafters. And he said the real problem with that is those road crews are only as smart as an ashtray, and that's only when they're sober. So he can never really count on them to do anything right. So his plan was he wanted to somehow put the belts on the floor to have the road guys throw the receivers up in the rafters wherever they're going to throw it, turn the whole system on, and then have the belts communicate with the rafters. And then he was hoping that there would be enough information in there to make everything work out so that I could calculate where everything is. That's why he gave me those equations that I just passed around. You want to determine the exact locations of all of the transmitting and receiving units based on knowing all of those interpoint distances. For him, then, it was very bad news that there wasn't going to be a unique solution, because even when he had everything thrown on the floor and up in the rafters, he still wasn't going to be able to figure out where everything was. I did point out to him that, okay, if I go back and I add one more piece of information, like, okay, let's fix a couple of these distances or set something at a 90-degree angle, that provides one extra constraint, which removes 1 degree of freedom, and then you could get everything down precisely. And he went back to his lab and he told his engineers, and they added those extra constraints, and they said, you know what, lo and behold, it works. Now, I had done all that just for the fun of it, but he wrote back and he said, you know what, I know, I just asked this just because I thought somebody might be able to help. He said, you did me such a nice job, I'm sending you $100 just to say thank you. And so there's my $100 of profit that I made from algebraic geometry. So with that, I think I'm going to finish. Anytime you've got some linkage problems, something about moving points, distances, triangulation, you come to me because I like to play with these things. Thank you for your help. Do y'all have any questions? Got any examples for me already? Yeah, go ahead.
If you're using this tomorrow, like a cybernetic arm or a limb, could you use it to like perfect like the way that they move so that it's less robotic? Because you know how like you want to have an arm that is more functional,
right?
In a way. So could you use that in a sense?
Yeah, it's kind of subtle the way that sort of thing works. I mean, like when you start modeling a robotic arm, one of the things that you notice is, okay, all I need to do is I need to change this angle. That's one of the things that I can do. I mean, we know the degrees of freedom and so on, and geometrically we see that all we need to do here is to keep track of this angle. Well, when you make a robotic arm, then the natural thing is you put one little pulley in here and it changes the angle. But the problem with that is it feels robotic sometimes, because you turn it on and you say, okay, adjust the angle, and it goes, and it's very kind of jerky, right? And the human body doesn't do that because it has like backup systems. So you have the, what is it, biceps and triceps, right? So two different muscles that kind of regulate each other. And so it's, the mathematics of getting into the right position is already known. When you decide that you want to make it be a little smoother, then now you're talking about questions of, well, how do you like regulate that motion? It's the same thing here on the Stewart platform. If you tell me exactly the configuration you want to get in, then I will know what those 6 lengths need to be. Okay, but do I change the lengths like one at a time and then have the guy do all of this? Or is there going to be a gradual way that kind of mimics a more natural thing? So then you have to describe what would be your objective function. What is it you're trying to optimize? Like in the case of the Stewart platform, I might shoot for I don't know, change a minimal distance through SO3 so that the person feels the least amount of change in orientation. I don't think translations bother people so much as a change in orientation. So once you put in a constraint of something to be minimized, then you play with your extra variables, your extra degrees of freedom. So yes, by all means, these things, people are working on these things. And they've done really nice jobs, like the poor guys that come back needing prosthetic limbs from the wars. They've got really nice stuff going now, so it's getting a lot better. Other questions?
Can you modify the machine so the guy can go upside down?
I thought about that. So SO3 it's a non-trivial group. I showed you that there are these non-trivial paths inside SO3. And that means that these functions that go back and forth, they can't be globally defined in a one-to-one way. Well, that's part of what I said here, is that there can be 40 different positions to match every combination of the lengths, up to 40. So then it's like, well, gee, we're not really sure what you can do what pieces of the configuration space are actually going to be connected to which other ones, especially once you put in the constraints of how to avoid the crossing arms and things like that. As far as I know, you can turn the thing upside down if you if you take off the platform at the top and you just replace D, E, and F with, the line segments D, E, and F, just put bars there instead of the platform. That way you have minimal need to cross things. And then I think what you do is, if you lower, let's see, if you lower the point F, keeping D and E approximately where they are, then you can actually swing point F all the way over to the other side. So you can get the guy turned upside down. You can't go you can't make a full 360-degree loop. I think that's true, because I think then you'd be trying to make a closed loop that's the 360-degree rotation that's non-trivial inside this group. So yeah, I don't want to be the person who has to experiment with the upside down thing. I will tell you though that, so I've actually seen these things in motion. I'm the kind of guy who goes to the fun halls, and everyone else wants to climb in, and I always want to look underneath, see how it works. So I went to one once where they were advertising this virtual reality roller coaster, and I thought, oh, they're going to do this. Well, they didn't. They had a different set of 6 variables. Instead of modifying those 6 lengths, they had some other thing where the whole device was going to spin around on one axis, and the device internally had another axis that would allow it to spin you around this way. So they were choosing other things to be the constants instead of just these distances. And I was reminded of those when I was getting ready for this talk. I went online. Look it up. Look for virtual reality roller coaster, and you'll see that there's this big red thing in the video that I saw, and people climb in and they get completely spun around along more than one axis. What do they call it in aviation? You got yaw, pitch, and roll. So 2 of them are just built into the machine, and I don't know if you can accomplish the 3rd one. But it's, yeah, this isn't the only kind of platform that you can make to spin people around.
I'm wondering whether we can use these algebraic and geometric models for solving real-world economic problems.
Well, I wish I knew, because I got to save money in my 401k, and if I could fiddle with the constraints and make a lot of money. To some extent, that's true. I mean, the virtue of the things that I've been talking about today is that I can take the geometry problems and write them down with polynomial equations. And I know enough about polynomial equations to be able to give definitive answers to how many solutions there are and that kind of a thing. So what kind of equations are you going to write down for economic problems? I mean, people will model the US economy, for example. What's that called? The Leontief model or something like that. It was one of the early Nobel Prizes, I think. And you sort of notice that, for example, the unemployment rate seems to vary with respect to the federal interest rate. And in turn, the federal interest rate seems to vary with respect to the current home ownership rate or something like that. So they can keep track of millions of variables, and over time, people notice that some of these variables tend to be related. So there was something called the Laffer curve, and it's not a joke, it's L-A-F-F-E-R. But it was something like, I think I've got the right one. Maybe that's not the curve, but there's basically an inverse relationship between unemployment and inflation rate. And so if you want a low inflation rate, you're going to have a high unemployment rate. That's kind of what we see now. So people will find these kind of relationships. So what would this mean? X times y equals 1 or something, right? But of course, these are all just approximations. Most of the relationships you get between curves between the economic variables, they just tend to be of the form y equals mx plus b. I mean, locally, every differentiable function can be expressed this way. And all of these approximations are local anyway, because no one ever considers what happens if suddenly the unemployment rate is 50%. You know, we've only got things that are formulas that are going to work for small perturbations of our current reality. So econometrics is the study that you're talking about, and people are working on it, and they can do things that are pretty good, but it's all local, which means that everything turns into linear algebra, and now it's a linear optimization problem or something like that. So yeah, I mean, that's what game theory is about, right? All that kind of linear programming stuff. Those were based on economics in the first place. But I don't know if we have concrete formulas to play with in the same way that we did here. It's too bad.
I think we're done. So does everybody want to thank our speaker again?
My pleasure.
Pizza's upstairs.